Welcome back. In this video, we are going to solve problem 14-25 that is taken from chapter number 14, Energy Methods, and book name is Mechanics of Material by R.C. Hibbeler. So statement is determine the horizontal displacement of joint B, the member of truss RE992 steel bar, each with a cross-sectional area of 2500 square millimeter. So you can see this is a truss and there is a load of 15 kilonewton applied at point B. So you have to determine due to this load, this point B will move toward this. So this is the horizontal displacement of point B. So you have to find this displacement of point B. So let's start with the solution. So this topic comes under the category of conservation of energy, and you know that due to this external load, this point B will move to this distance, clear delta B, which is the external work, because force into this distance is work, which is the external work that is stored in the form of strain energy. So this strain energy, external work due to external load will be stored in the form of external strain energy that will be equal to the axial strain energy in this truss. So the main basic equation is this one. So we'll apply this equation. So let's start with the solution. So first step is that you have to find the forces in each member of truss by using my method of joint. Why? Because we should know the axial load in each member so that we can apply the strain energy due to axial loading. So first what we will do is that we will take joint B. So you can see this is joint B. So due to this load, this will cause this member to compress. As a result, this member will exert load FAB on point B is in this direction. Similarly, due to this point B will move, this will be in elongation. As a result, this member will apply load in this direction, which will be FBD. So I will draw it. This is point B, clear? So this is the load, which is 15 kilonewton. The member FAB will apply load in this direction, FAB. And the member FBD will apply load in downward direction, clear? So we'll find this by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along x direction must be equal to 0 and force in towards right is positive. So plus FAB minus 15 is equal to 0. So FAB is equal to 15 kilonewton. Now you can see that this is the force that this member applies on joint B. As a result, the force in this member will be compressive one. Clear? So I will write it this way. This is in compression. This member FAB is in compression. Now we'll apply another equation that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So you can see only force FBD is acting. There is no other force. So it means that FBD is equal to 0. Okay. Now this is for joint B. Okay. We will move toward joint A. So you can see this is joint A. This is joint A. So this member is exerting a force on joint A is this. This is FAB. Now, due to this load, this member will exert force in this direction. This will be FAD. And this member will also exert a force in this direction. This will be FAC. Clear? So we will draw the free body diagram. This is point A. You have this FAB, which is in this direction. So FAB is, we have calculated that is 15 kilonewton. Clear? So this is FAC, which is not known. Clear? And this load is FAD. Okay, now you can see this length is 2 and this is 1.5. So if I draw a right angle triangle over here, clear? So this is right angle triangle. If I multiply it with 2 and this with 2, so this become equal to 4, this will become 3 and this will be 5. So this is standard right angle triangle. So I will draw this right angle triangle over here as well so that we can get its horizontal and vertical component, 4, 3 and 5. Now we will apply equation of equilibrium. So what is the equation of equilibrium is that sum of all forces along x direction must be equal to 0 and force toward right side is taken as positive. So FAB, which is minus 15. Now you can see this will have two components. One is this one, another one is this one. So I will draw it by using two colors, different color. One is this component and other one is this component. So this component will be equal to FAD into 4 over 5. Clear? And this component is equal to FAD 3 over 5 because this is perpendicular. How? Because you can see this is theta. So if you take sine theta, so sine theta is equal to 3 over 5 and cos theta is equal to 4 over 5. So this is the horizontal component which is equal to FAD, x component which is equal to FAD cos theta. So if you replace cos theta, so it will be equal to FAD 4 over 5. And same here, this is equal to FAD sine theta and sine theta is 3 over 5. Now you can apply equation of equilibrium. So this plus FAD 4 over 5 is equal to 0. So from here, FAD will be equal to 4 over 5 is equal to 15. So FAD will be equal to 18.75 kilonewton. Okay. This FAD will be in tension. Why? Because you can see due to this load, clear, there will be elongation in FAD. So this FAD will be in tension. Okay. Now we will move toward finding another force that we will apply. Sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So from here, FAC minus FAD into 3 over 5 is equal to 0. So you can see FAD, we have F value, FAC is equal to FAD into 3 over 5. So FAD is 18.75 into 3 by 5. So when you solve this, you will get FAC comes out to be 11.25 kilo Newton. Okay. Since this force is FAC is applying force in this downward direction, okay, upward direction. So the force in this member FAC will be in downward. That means it is in compression. The previous one was about this FAD. Okay, so make a correction over there. So I will write here this is in compression. Now we'll move toward joint C. So we will find the forces for joint C. Joint C. So you can see that this is your joint C. This is your joint C, where you have a normal force Cy clear, and there is a downward force which is FAC we have calculated, and this FCD will be in this direction. So we will draw this joint C so that this is your point C. So upward reaction force is Cy clear, the downward force is FAC clear, and the horizontal force is FCD. Okay, so we know this, we do not need this because this we are only finding the forces in members. So we will apply equation of equilibrium that sum of all forces along x direction must be equal to 0 and force in this direction is taken as positive. So there is only horizontal force FCD, there is no other force, so it means that FCD is equal to 0. Now you can check it that we have how much member 1, 2, 3, 4, 5, and we have find the 5 forces 1, 2, 3, 4 and 5 forces in each member. So what we are going to do is that we will find the strain energy due to axial loading, and that is equal to sum of n square L divided by 2 AE. So what we are going to do is that we will take 1 over 2 AE outside, and we will left with sum of n square multiplied by L. So for 5 different member, I will write 1 over 2 area is given as 2500 into 10 to the power minus 6. So 2500 into 10 to the power minus 6 into E. E is 200 gigapascal into 10 to the power 9. You can check it from the property table. Let me show you. You can see for A992 E is 200 gigapascal. Okay. Now what we will do is that we will multiply forces in each. So starting from this force FAB 15 kilonewton. So FAB is 15 kilonewton, 15 into 10 to the power 3 whole square multiplied by length of AB, which is 2 meter. 2 meter. So I will write it multiplied by 2. Plus the second force is FBD, which is 0. So 0 square multiplied by length of FBD is 1.5. So 1.5. Plus third force is this one, which is FAD. So FAD is 18.75. 18.75 into 10 to the power 3 multiplied by its length. So its length will be 5 by using Pythagoras theorem. Okay, not 7.5. This is 2. This is 1.5. So it will be 2.5 meter. Okay, so multiply by 2.5. Plus the fourth force is this FAC. So 11.25 into 10 to the power 3 whole square multiplied by length of AC. So AC is length 1.5 meter. So I will write 1.5 meter. And the last force is FCD, which is 0, and 0 multiplied by its length will be 0. So when you solve this, you will get the strain energy due to axial loading comes out to be, it will be 1.51875 joules. Now this is the strain energy due to axial loading, and we will find the strain energy due to external work, which will be equal to this external force and the displacement delta H, horizontal displacement of delta B. So that will be equal to 15 into 10 to the power 3 multiplied by delta H of B. Now by using law of conservation of energy, we will use this equation that UE is equal to UAI. So just put the value 1.51875 is equal to 1.5 into delta HB. Okay, one more correction is that due to this external work, this formula is 1 over 2 multiplied by load into the horizontal displacement. So make correction over here that UE is equal to 1 over 2 external load P into horizontal displacement. So I will write 1 over 2 as well over here. Clear? And from here, you will get delta HB will be equal to 2 multiplied by 1.51875 divided by 1.5. and that comes out to be 0.2025 into 10 to the power minus 3 meter. Or you can see that horizontal distance or displacement of point B will be equal to 0.2025 millimeter, which is the answer of our this question. And as we know that 1.5 kilonewtons, so I will multiply it with 10 to the power 3 as well, so that you should have this answer. And this was all about this problem 14-25. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also share my videos with your friends and help me in growing further. Thank you for watching. Welcome back to another problem, that is 14-26. This problem is taken from chapter number 14. Chapter number is 14 and it is energy method, and book name is Mechanics of Material by R.C. Hibler. So statement is determine the vertical displacement of joint C. A is constant. So you can see this is a truss where this is joint C, where P load is applied, and the length of AC is L as well. BC is also L, and the product of A is constant. So due to this load, this joint C will move downward, that is cover this delta C. So you have to find this delta C. So let's start with the solution. So we know that due to this load, this joint C will move downward and it will cover this distance delta C. So due to this load, external load, we have strain energy due to external load, and that is equal to 1/2 P times this displacement delta C. And then we will find the strain energy due to axial loading, and we will, as this external work is transferred to internal work, so strain energy external due to external load will be equal to strain energy due to axial load. So we will use this equation. So for finding this, we will find the forces in each member, which is member AC and BC, by using method of joint. So first we will find these two forces. So what we will do is we will take joint C. Okay, so again you can see this is your joint C, clear, and this is one load is this one, which is FAC, and this is horizontal axis, and another load will be also this one, which will be equal to FBC. So since you can see that this, what will be this angle? So if this will become equal to L by 2, clear. And what will be this length? We do not know this length. This is X and this is L. So let this is theta. So tangent of theta, we will use sine of theta. So sine of theta is equal to L by 2 divided by L, clear. So it will be equal to 1/2. So theta will be equal to sine inverse 0.5, which is equal to 30 degree. So this angle is 30 degree. So this will be also 30 degree. Clear? So this will be also 30 degree. Now we'll apply equation of equilibrium, that sum of all forces along x direction must be equal to 0 and force toward right side is taken as positive. So you can see FAC will have two components, one along this component horizontal and other will be vertical. Clear? Also you can see you have a P load acting at joint C, which is also represented as P. Okay, so this vertical component. So this vertical component will be equal to FAC sine of 30 degree, and this horizontal component will be equal to FAC cos of 30 degree. Similarly, this downward force FBC will have two components, clear. One will be in this direction, horizontal direction, and one will be in this direction. Okay, and this component will be equal to FBC sine of 30 degree, and this component will be equal to FBC cos of 30 degree. Now you can see FAC cos of 30 degree, this is in negative direction, minus FBC cos of 30 degree. So it means that FAC cos of 30 degree is equal to FBC minus FBC cos of 30 degree. So the cos of 30 will cancel each other. So it means that FAC is minus FBC. Clear? So what does it mean? It means that the direction we assume for FBC is wrong. It should be in this direction. Clear? Because they should be equal to each other in order to keep in equilibrium. So FAC should be, FAC is equal to FBC. Why? Assumed direction was wrong. Okay. Now we'll apply another equation of equilibrium, that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So you can see one force which is minus P, the other force is this one FAC, and since this direction is wrong, so this FBC will be in upward direction. It should be in upward direction because the assumed direction was wrong. It should be like this. So it will have two components. One is in this direction and the one is this direction. So I will write minus P plus FBC sine of 30 degree plus FEC sine of 30 degree is equal to 0. Since FEC is equal to FBC, so I will write P is equal to 2 times FBC sine of 30 degree. And from here, FBC will be equal to, FBC is equal to 2 multiplied by FBC, and sine of 30 is equal to 0.5, which will be equal to 1 multiplied by FBC. Okay, so this is equal to P. Let me correct it. This is equal to P. So it means that P is equal to FBC, which is equal to FAC. Now you have forces in each member, clear? So you can apply this equation for finding the strain energy due to axial loading, which is equal to sum of n square into L divided by 2AE. So 1 over 2A is outside. So we will write FAC square into LAC plus FBC square into LBC. Okay. So put the value 1 over 2AE FAC is equal to P. So P square multiplied by LAC is L, and BC is also L. So P square multiplied by L, and FBC is also P. So P square into L, which is equal to strain energy due to axial loading. So this will become equal to 2P square L divided by 2AE. Clear? So 2 will cancel, and we will get P square L divided by AE. Okay. Now what we will do is that we know that strain energy due to external load is equal to 1 over 2 P times delta C, which is written over here. You can see that is written over here. This is equal to UE is equal to UAI. So 1 over 2 P into delta C is equal to P square L over AE. Clear? So this will become equal to, delta C will become equal to 2P square L divided by P into AE. Okay, so it will be equal to 2PL divided by AE. So horizontal displacement of point C due to load P will be equal to 2PL divided by AE, which is the answer of our this question. And that was all about this problem 14-26. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also share my videos with your friends and help me in growing further. Thank you for watching. Welcome back. Problem 14-27. That is, this problem is taken from chapter number 14, Energy Methods, and book name is Mechanics of Material by R.C. Hibbeler. So statement is determine the horizontal displacement of joint A. The member of truss are A992 steel rods, each having diameter of 2 inch. So you can see this is the truss there that is composed of different A992 steel rods, and there is a load of 15 kips applied at joint A. So you have, due to this load, this point A will move horizontally, that is delta HA. So you have to find this horizontal displacement of joint due to this 15 kips load. So let's start with the solution. So we'll use conservation of energy. We state that due to this load, clear, this joint point A will move delta HA. So this energy is strain energy to external load is 1 over 2 P times this horizontal displacement A, that will be equal to the axial strain energy in this truss. So what we will do is that we know that this UE will be equal to 1 over 2 multiplied by 15, which is the load, into horizontal displacement of point A, which will be this one. Clear? This is delta H, horizontal displacement of point A. Now we'll find the strain energy due to axial loading. So that will be equal to sum of n square into L divided by AE. So here you can see we have 6 member, 1, 2, 3, 4, 5, 6. So what we are going to do is that we will find the forces in this member. Clear? So I will take 1 over, this is 2AE. Okay. So 1 over 2AE common out of this, and we will left with, for force AB, it will be equal to FAB square into length of AB plus FBD square into length of BD plus FAC square into length of AC plus F of CE square into LCE plus F of BC square into LBC, and the last one is F of CD square into LCD. So what we are going to do, we have to find these 6 different forces, clear, by using method of joint. So we will apply first for joint A in order to find these forces. So you can see this is joint A where you have 15 kips load. So due to this load, this member AB will apply load downward, and this member AC will apply a reaction force at point A in this direction. So I will draw it. This is point A. This is 15 kips load horizontal. Clear? The load that is this member AB apply at point A will be equal to FAB and this load will be equal to FAC, which will be like this, FAC. So this is 4 feet. This you can see is 3 feet. So by using Pythagoras theorem, this will be 5 feet. So again, here you will be having a right angle triangle, clear, 3, 4, and 5. Also, if you are confused, so you can take theta angle over here, and we will find this forces. So we'll apply first equation of equilibrium, that sum of all forces along x direction must be equal to 0, and force in this direction is taken as positive. So 15 kips load is applied, clear, that will be in positive direction, clear, and the other force that is applied is this horizontal component of this FAC, which will be in this direction, clear, and it will have 2 components. So let me draw these 2 components by using another color. So its one component will be this one, and other component will be vertical. So this component will be equal to FAC cos of theta, and this vertical component will be equal to FAC sine theta. Now cos theta from this right angle triangle, this is equal to 3 over 5, and sine theta is equal to 4 over 5. So I will write 15 minus FAC sine theta. Sine theta is 4 over 5. Clear? This is 4 over 5. Sine theta is okay. We will apply this equation. This is 3 over 5 cos theta. So 3 over 5. Let me correct it, because this is horizontal component. 3 over 5 is equal to 0. So from here, this FAC will be equal to 25 kip. Now you can see that this member is applying force in this direction, clear, at this point. As a result, this member will be, the force in this member will be in this direction. So it means that this member is in compression. So I will write here C. Now we will apply another equation of equilibrium, that sum of all forces along y direction must be equal to 0, and upward force is taken as positive. So you can see FAB is downward. So minus FAB plus the vertical component, which is FAC sine of theta, and sine of theta is 4 over 5 is equal to 0. So I will get FAB is equal to FAC, which is 25, into 4 over 5. And when you calculate, it will give you 20 kip. So I will write FAB is equal to 20 kip. Okay. You can see that this force FAB is downward. So as a result, force in this member AB will be upward. So it means that member AB is in tension. Clear? So we have now find this FA and FC. Now we will move toward joint B. So I will take joint B. Joint B. Okay. So let me show you this force on joint B. This force by member FAB on joint B will be this direction. This FBD will be in downward direction, and this FBC will be in this direction. You can also assume it. So this is your point B. Clear? Here you have FAB in upward direction, which is 20 kips. Clear? FBD is downward. FBD is downward, which is not known, and FBC is in this direction, which is also not known. So we'll find this by using equation of equilibrium, that sum of all forces along x direction must be equal to 0, and force toward right side is taken as positive. So only FBC is horizontally acting. There is no other force. So it means that FBC is equal to 0. Now we'll apply another equation of equilibrium, that sum of all forces along y direction must be equal to 0, and upward force is taken as positive. So you can see 20 is upward. So 20 minus FBD is equal to 0. So from here, this FBD is equal to 20 kips. Okay. So this FBD, you can see it is downward. So it means that force in member BD is in upward direction. So it means that BD is in tension. So up till now we have 4 forces, 1, 2, 3, 4. Now we'll apply method of joint using joint C. So this is your joint C. Here you can see the forces will be this one, this one, this one, and this one. So I will draw the free body diagram over here for joint C. So for joint C. So let this is your point C. Clear? This is your point C. So at this you have this FAC, which we have calculated 25 kips. Clear? Here you have this force along this direction, FAC. This is FCE, which is not known. Clear? You have horizontal BC, FBC, which we have calculated 0, and you have force FCD. FCD. Okay. You can see that what we will do here is that if you take this axis as your x dash axis, x dash, and this your y dash axis. Clear? We are interested to find out this FCD and FCE. Clear? These are only unknown forces. So what we will do is that first we will find the force, the sum of all forces along x dash direction must be equal to 0, and force in this direction is taken as positive. So let this is making angle theta. So it will have 2 components. One is this one, and other one is this one. So this component will be equal to FCD cos of theta. So I will write FCD cos of theta, and there is no other force along x direction. Clear? So it means that this is equal to 0. So it means FCD is equal to 0. Also, we will apply another equation of equilibrium that sum of all forces along y dash is equal to 0 and force in this direction is taken as positive. So you can see one is minus 25 and other one is plus FCE is equal to 0. So from here, FCE is equal to 25 kip. Okay. All these 6 forces, so you can just put it in this formula. I will apply it over here. So strain energy due to axial loading is equal to 1 over 2. Area diameter is given, so pi by 4. D square, D is 2 inch, so 2 square, multiply by E. So E for A992 for US customary will be this one. Let me show you. It will be 29 into 10 to the power 3 KSI. So I will write 29 into 10 to the power 3. Now multiply FAB. Let me show you. This is 20 kips. So 20 square into length of AB. AB is 4 feet. So in inch, it will be 4 multiplied by 2, 12. So 4 multiplied by 12, we convert it into inch. Plus FBD. FBD is 20 kips. So 20 square multiplied by BD, length of BD is also 4. So it will be 12 into 4 inch. So 12 multiplied by 4 inch. Plus the third one is FAC. So FAC, where is FAC? FAC is, FAB is 20, FBD is 20, FAC is 25. So 25 square multiplied by AC. So length of AC is 55 feet, which is 12 into 5 is 60 inch. Clear? So 12 into 5 plus FCE. FCE. So F, where is FCE? Where is FCE? FCE is this one. Okay, this is FCE. You can see this is FC 25. So plus 25 into length. This length is also 5 feet by using Pythagoras theorem. So 5 into 12. Clear? Plus FBC. FBC is 0, so it will be 0. The whole term will be 0. And FCD. So FCD is also 0. It will be 0. Clear? So when you solve this, you will get strain energy due to axial loading will comes out to be 0.6224 kips into inch. Now you have this loading, so you can go to the conversion of energy and you will use this formula. You know that external work is this, so strain energy due to external work is this. Let me write it. UE is equal to UAI. So 1 over 2, 15. The load was 15 kips. So 15 into horizontal displacement of point A is equal to UAE, which is this one, 0.6224. So delta H, horizontal displacement of point A, comes out to be 2 multiplied by 0.6224 divided by 15. Clear? And when you solve this, you will get, let me calculate, you will get delta H, horizontal displacement of point A, comes out to be 0.0829 inch, or you can say 0.83 inch, which is the answer of our this question. And that was all about this problem 14-27. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also share my channel with your friends and help me in growing further. Thank you for watching. Welcome back. Problem 14-28. This problem is taken from chapter number 14, Energy Methods, and book name is Mechanics of Material by R.C. Hibbeler. So statement is determine the vertical displacement of joint C. The member of truss are 2014 T6 aluminum 40 millimeter diameter rods. So you can see this is the truss that is composed of 2040 T6 aluminum. The diameter of each rod is 40 millimeter, and there is a point load of 30 kilonewton at point C. So this, due to this load, this point C will move downward. So this is the vertical displacement of point C, which we have to find. So you can see the given data, all the diameters are equal, which is D, and that is 0.04 meter. Length of AB and BC are 2 millimeter, BD is 1.5 millimeter, and by using Pythagoras theorem, this will be also this will be 2.5. I think this is 2.5. Yes, this is 2.5. So we will correct it. This is 2.5. So I will write it 2.5 meter. So you have to find the displacement C. Let this C will move this distance. So this is del C. Now we know that using conservation of energy, this formula UC is equal to UAI. Now what is UC? So you can see this is 30 kilonewton. So this external force will do work which is equal to UC, and this work is stored in the form of strain energy. So external work done is equal to UC, and that will be equal to 1 over 2, 30 kilonewtons. So it will be 30 into 10 to the power 3 multiplied by this delta C. And what about UAI? So we will find UAI, and we know that UAI is equal to sum of n square L divided by 2AE, where En is axial load in this each member. So for every member, we have to write 1 over 2AE. So you can see we have 1, 2, 3, 4, 5 member. So I will write FAD square into length LAD plus FDC square into LDC plus FBD square into LBD plus FAB square into LAB plus FBC square into LBC. So what we are going to do, we are going to find these forces FAD, FCD, FBD, FAB, and FBC by using method of joint. So what will be the first step is that we will take this joint C. So we will take joint C and we will draw the free body diagram. Now you can see due to this load, this is joint C. So this member FBC will exert force in this direction, and this member BD will act force in this direction at point C. Clear? So I will draw it. This is point C. This is 30 kilonewton load. 30 kilonewton load. This is FBC, which is in this direction. This 30 FBC, and this load will exert this direction force. This is FCD or FDC. Now you can see this is 2 and the vertical height is 1.5. So if I draw a right angle triangle over here, so this is 2, this is 1.5. So by using Pythagoras theorem, this will be 2.5 meter. Now we'll apply equation of equilibrium. So first equation of equilibrium is that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So you can see minus 30, which is downward, plus this component will have two forces. One is along x-axis, and another one is along y-axis. And this component will be equal to FCD sine theta, and this component will be FCD cos theta. And what is theta? So if theta is this one, so theta is cos theta will be equal to 2 divided by 2.5. Clear? And sine theta will be equal to 1.5 divided by 2.5. Okay, so the vertical component is plus FCD sine theta is equal to 0. So FCD sine theta is 1.5 divided by 2.5 is equal to 30. So from here, this FCD will be equal to 50 kilonewton. Now you can see that this FCD is in this direction. As a result, this force in this member FCD will be in this direction. Clear? And it means that FCD is in tension. So I will write T. Now we'll apply another equation of equilibrium that sum of all forces along x direction must be equal to 0 and force toward right side is taken as positive. So FBC is in right direction minus FCD cos of theta is in opposite direction. Their sum must be equal to 0. So FBC is equal to FCD cos of theta. So FCD is 50 and cos of theta is 2 divided by 2.5. And when you solve this, you will get this FBC will be equal to 40 kilonewton. Now you can see that this force FBC is in this direction. The member applying force at point C is in this direction. As a result, Newton's third law, this FBC will be in compression. So I will write it here as compression. Now we have this force. We will move toward another joint C, that is joint D. Sorry, another joint which is joint D. Let me show you. This is the joint D. You can see the force at this joint will be, this force will be in this direction, because here you can see you have taken this in upward. As a result, this force will exert in this direction. Similarly, FAD will be in this direction and FBD will be in upward direction. You can also assume and you can do the method of joint at this point. So FBD is an upward direction. This is FBD. Clear? This one member is this FCD, which is 50. FCD is equal to 50 kilonewtons. Clear? And this FAD, which is not known. This is FAD is not known. So again, you can see the ratio of their side. Here you'll be having right angle triangle 2, 1.5 and 2. So same is the here 2, 1.5 and 2. So I will draw the same right angle triangle on both sides. So this is 2, 1.5 and 2.5. So you will have the same over here 2, 1.5 and 2.5. Now we will have two component of this force, one along y direction and other along x direction. Similarly, it will have two component. One is this and another one is this one. So this component will be equal to FCD into cos of theta. So cos of theta, if theta is this one, so cos of theta is equal to 2 divided by 2.5. And this component will be FCD sine of theta, which is 1.5 divided by 2.5. And same is the case here. This will be FAD cos theta, which is 2 divided by 2.5. and the vertical component is FED sine theta, which will be 1.5 divided by 2.5. Okay, now you can apply the equation of equilibrium. So first equation of equilibrium is that sum of all forces along x direction must be equal to 0 and force in this direction is taken as positive. So you can see two forces acting horizontally. One is this one and another one is this one. So FAD into 2 over 2.5 minus FAD plus FCD into 2 over 2.5 is equal to 0. So FAD into 2 divided by 2.5 will be equal to FCD into 2 over 2.5. So these two terms will cancel. So we will get FAD is equal to FCD. Now what we will do is that we will apply another equation of equilibrium. And again, if you further simplify it, you can see FCD is 50. So from here, FAD will be also equal to 50 kilonewton. Okay. Now moving toward another equation of equilibrium, that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So you can see FBD is acting upward. So FBD minus the vertical component, these two, these are minus. So FAD is 50. Let me write 50 into 1.5 divided by 2.5. Minus 50 into 1.5 divided by 2.5 is equal to 0. And again, when you solve for this FBD, so FBD will be equal to 60 kilonewton. And you can see the FBD is acting upward. This force acting upward, this FB force member BD is applied upward force on this D. So as a result, this member FBD will be in compression. So I will write it C. Clear? And FAD was in tension. Why? You can see that FAD is in this direction. So as a result, this force in this member will be in tension. Now we have four forces, 1, 2, 3, and 4. So there are total 1, 2, 3, 4, 5 members. So we have to find one more force. So what we will do is that we will take this joint B. Clear? And we will apply the equation of equilibrium. So you can see this FBD, the force this member BD will apply at point B will be this one. Clear? Similarly, FAB will be this one. FBC will be this one. And there is a roller support which apply force which is BY. Clear? So we will apply equation of equilibrium by using method of joint at point B. So joint B. So this is joint B. So you are having a vertical force of FBD which is 60 kilonewton. You have a vertical reaction force due to roller support, that is BY. FAB is the horizontal force that member AB exert at point B, and FBC which is 40 kilonewton. Now you can apply equation of equilibrium. So only we need FAB. So we will apply equation of equilibrium that sum of all forces along x direction must be equal to 0 and force toward right is positive. So FAB minus this FBC which is 40 is equal to 0. So it means that FAB is also equal to 40 kilonewton. And you can see that FAB is toward right direction. So by Newton third law, the force in member AB will be in this direction. So AB will be in compression. So I will write FAB is in compression. Now you have all the forces. So what we are going to do is that we will put it in this formula. So let me put it over here. UA due to I is equal to 1 over 2A. What is A? So area of is for rod is pi by 4 D square. So D is 0.04. So 0.04 square. And what is E? So E for A992. Okay. So I will go to the property tables and you can say you have this table SI unit. So here you can see that for 2014 T6, this is 73.1 in gigapascal. 73.1 into 10 to the power 9. Clear? Multiply by FAD. Now where is FAD? So you can see FAD is this one, which you can see FAD is 50 kilonewton. So I will write 50 kilonewton. So 50 into 10 to the power 3 whole square into length of AD. Length of AD is 2.5. So 2.5 plus FDC. So FDC is also 50, you can say, and FDC is 2.5. So instead of writing it again, so I will just multiply it with 2. Clear? Plus FBD. So FBD is this one, 60 kilonewton. So I will write 60 into 10 to the power 3 multiplied by length is 1.5. Clear? Plus you can see that FAB and FBC both are same. FAB and FBC. Both are same. So I will write 2 times 40 kilonewton into length, and the length is BC, 2 meter. So I will multiply it with 2. Okay. Now when you calculate it, you will get strain energy due to axial loading will come out to be, let me calculate it, it will come out to be 132.27 joules. Also note that there is 4 square, so 60 whole square and 40 into square. So let me correct it as well over here. This will be whole square and this will be also whole square multiplied by 2. Okay, now it is fine. So you will get strain energy due to axial loading will be this one. Again, using conservation of energy, we know that UE is equal to UAI. So UE was this one, 1 over 2, 30 into 10 to the power 3, 1 over 2, 30 into 10 to the power 3 multiplied by delta C is equal to 132.27 joules. So delta C will become equal to 2 multiplied by 132.27 divided by 30 into 10 to the power 3 will give you vertical displacement of point C, and that will be equal to 8.818 into 10 to the power minus 3 meter, or in millimeter it will be 8.82 millimeter. So this is the vertical displacement of point C due to load 30 kilonewton. So this is 8.82 millimeter. And that was all about this problem 14-28. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also share my videos with your friends and help them in learning as well. Thank you for watching. Welcome back. Problem 14-29. This problem is taken from chapter number 14, Energy Methods, and book name is Mechanics of Material by R.C. Hibbeler. So statement is determine the displacement of point B on A992 steel beam. I is 250 inch power 4. So you can see this is a cantilever beam, clear, having a point load at point B, which is 8 kips, clear. So total length is 25 feet. So due to this load, this beam will deflect like this. So you have to find this vertical displacement of this point B, which is delta B, clear, due to this load. So let's start with the solution. So we know that due to this load 8 kips, this point B, let's move toward this point. So this displacement is delta B here, and we can find this delta B by using, due to this external load, we have strain energy stored, which is UE, and that will be equal to 1 over 2 multiplied by load, which is 8, into displacement where it is moved, and that is delta B. And due to law of conservation of energy, due to law of conservation, not conversion, conservation of energy, this external work is stored in the beam in the form of strain energy due to bending, because you can see due to this load there will be a bending in this beam. So UE will be equal to U bending, strain energy due to bending. Now we'll find the strain energy due to bending. So how you will find is that for that you have to cut the beam over here, clear, and you will take this right portion. And what will be the X? So X will be the distance from point B. So this will be your X, clear, and we will draw the free body diagram. So let me draw it. This is point C, this is your point B, where you have 8 kips load here, and this is your X. The range of X will be, X start from here 0 till X is 15 feet, or 15 multiplied by 12, and unit will be inch, clear. So when you cut it, you will be having a shear force and you will be having a moment M. Let this is point O. So what we will find this moment by using equation of equilibrium, that sum of all moment about point O is equal to 0, and taking the counterclockwise moment as positive. So about point O, one moment is this counterclockwise moment, which is M. So I will write plus M. And the second moment is due to this 8 into perpendicular distance is X, and this is producing clockwise movement, so it will be negative. So minus 8 into X, and sum of all these moments will be equal to 0. So it means that this reaction moment will be, your internal moment will be equal to 8X, clear? And X is either you take in feet or inch, but we will take this in feet, inch. We know that bending strain energy is equal to integral from 0 to L m square dx divided by 2EI, clear? So you can put the value 1 over 2e into I. Integral from 0 to L. What is m? So m is 8x, so 8x square into dx. Okay, that will give you bending strain energy. Now this bending strain energy is equal to 1 over 2ei integral 0 to L. So this is 64x square into dx. And if you further simplify, it will be 1 over 2ei, and 64 will come out. So we'll left with 0 to L x square dx. Okay, so that will be 32 over EI, clear, and integral of x square will be x cube divided by 3 and limit from 0 to L. Okay, now 32 divided by EI, and if you put the limit, so you can see L will be equal to 15 into 12, 15 into 12, and it will be in inch. So I will write 15 multiplied by 12 whole cube minus 0 cube divided by 3. Okay, that will give you strain energy due to bending. Now what about E? So we have given A992 steel. So we know that from property table, E value is 29 into 10 to the power 3 KSI. Let me show you here. We will go to the property table. This is the property table for US customary. You can see that E992 steel, it is 29 into 10 to the power 3 KSI. So I will write it over here, the value of E. So 32 divided by 29 into 10 to the power 3 multiplied by I is given as 250. So 250 multiplied by this 3 into 15 multiplied by 12 whole cube. So at the end, what you will get is you will get the strain energy due to bending. Clear? Now we have use conservation of energy. UI is equal to UBI. So what is UBE? That is this one, 1 over 2 8 multiplied by delta B is equal to this term 32 divided by 29 into 10 to the power 3 multiplied by 250 multiplied by 3 multiplied by 15 multiplied by 12 whole cube. And when you solve this delta B, so delta B will come out to be 2.15 inch. Here, so this is the vertical displacement of point B due to the applied load on this cantilever beam. And that was all about this problem 14-29. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also share my videos with your friends and help me in growing my channel further. Thank you for watching. Welcome back. Problem 14-30. This problem is taken from chapter number 14, Energy Methods, and book name is Mechanics of Material by R.C. Hibbeler. So statement is determine the vertical displacement of end B of the cantilever 661 T6 aluminum alloy rectangular beam. Consider both shearing and bending strain energy. So you can see this is a cantilever beam having a point load 150 kilonewton at end B. The cross section of this cantilever beam is rectangular. Height is 300 millimeter while width is 100 millimeter. So you have to consider both shearing and bending strain energy, and then you have to find the displacement of this point B, which is delta B. So you can see due to this load, this beam will bend like this. So this will be the delta B, which we will have to find. So let's start with the solution. So we know that total strain energy, including shearing energy, will be UI due to shear plus strain energy due to bending. So we'll find this strain energy due to shearing as well as strain energy due to bending. For that, I have to cut this beam at a distance of X from this end B, clear, and we will draw the free body diagram. So let me draw the free body diagram. This is the beam. This is the distance X. This is point B having a point load of 150 kilonewton. So when you cut this beam, you will be having a shear force and you will be having a moment M. At this is point O. So we'll first find this moment by using equation of equilibrium, that sum of all moment about point O is equal to 0 and taking the counterclockwise moment as positive. So about point O, one moment is due to 150 and perpendicular distance is X, and this is producing clockwise moment, so it will be negative. So I will write minus 150 into perpendicular distance X. The another moment is due to this external reaction moment, which is counterclockwise and is taken as positive. And sum of all this moment about point O is equal to 0. So from here we will get moment is equal to 150 times X. Now what will about shear force? So we'll also find this shear force by using equation of equilibrium, that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So V minus 150, that is in kilonewton, into 10 to the power 3 is equal to 0. So from here we will get the shear force equal to 150 into 10 to the power 3 Newton. Okay. Now you have both this value. So what we will do is that we will first find the shearing strain energy. So shearing strain energy. So we know that strain energy due to shear, vertical shear, is equal to integral of 0 to L Fs V square into dx divided by 2Ga. This is the formula. And what is Fs? So Fs is form factor. Fs is equal to form factor. And for rectangular shape, this Fs is equal to 6 by 5. And what is about G? So G is modulus of rigidity. We'll find it from property table, and A is the area. So you can see the height is 300 and width is 100. So 300 in meter is 0.300 and width is 0.1. So this will be the area. Okay, now for G we'll go to the property table, and you can see here that this is the property table, and we have 6061 T6, 6061 T6, and G is 26 gigapascal. So we'll write the value 26 gigapascal, 26 into 10 to the power 9 Pascal. Okay, now we have all the value. V is there, all the values there, so you can just put it 0 to from L, and X start from 0 to X start from till 1. So 0 to 1, Fs is 6 over 5 V square. So V is 150 into 10 to the power 3 whole square into dx divided by 2 times G is 26 into 10 to the power 9, and area is 0.3 multiplied by 0.1. That will give you strain energy due to shear force. So when you calculate this, so you will get strain energy due to shearing comes out to be 17.31 joules. So this is the strain energy due to shearing. Now we'll find the strain energy due to bending. Strain energy due to bending. And we know that strain energy due to bending is equal to integral from 0 to L m square dx divided by 2EI. What is the value of E? So E can be taken from this table. Again, you can see E is 68.9 gigapascal. So I will write E is 68.9 into 10 to the power 9 Pascal. And what about I? I is the second moment of inertia for this rectangular section. It is equal to 1 over 12 breadth, which is 100 millimeter, and that in meter is 0.1, and height is 0.3, and it will be Q. So when you calculate it, will give you 0.225 into 10 to the power minus 3 meter power 4. There. So you can just put it in this formula. Strain energy due to bending will be equal to integral from 0 to L. Moment is 150. You can see 150 into 10 to the power 3 x. Clear? Why 150? Because the unit will be kilonewton into meter. So in order to convert into Newton into meter, we will multiply 10 to the power x into whole square into dx divided by 2EI. E is 68.9 into 10 to the power 9, and I is 0.225 into 10 to the power minus 3. Okay. Now, if you further simplify it, and you will get, if you take all these constants, 150 into 10 to the power 3 whole square divided by 2 multiplied by 68.9 into 10 to the power 9 multiplied by 0.225 into 10 to the power minus 3 integral of 0 to L, and L will be 1 because you can see x start from 0 till x is equal to 1. We are left with x square dx. And again, when you solve this, you will get this value 725.689 integral of 0 to 1 x square into dx, and that will be 725.689. This will be x cube divided by 3 and limit from 0 to 1. So that will be 725.689 into 1 cube minus 0 cube divided by 3 will give you strain energy due to bending. And lastly, when you solve this, you will get the strain energy due to bending comes out to be 241.90 joules. Now this is the strain energy due to bending. So strain energy due to shear is this, and strain energy due to bending is this. So we know that total strain energy, which is UI, is equal to UI due to shear plus UI due to bending. So add them both, 17.31 plus 241.90, and that will give you 259.20 joules. So this is the total strain energy. Now we will move above, and you can see due to this load 150, this beam will deflect like this. So its original axis. So this is the distance delta, that delta B will move, vertical displacement of delta B. So due to this external load, we have due to this external work will be done, and the work done will be stored in the form of strain energy, which will be equal to 1 over 2 this load 150 into 10 to the power 3 multiplied by this delta B. Clear? So I will write it, strain energy due to external load slash work will be equal to UE, and that will be equal to 1 over 2, 150 kilonewton was the load, into delta B. Okay, now we have both these equations. So by conservation of energy, This external work that is done on the object will be stored in the form of internal strain energy. So UE will be equal to UI. So UE is 1 over 2 into 10 to the power 1 over 2 into 150 into 10 to the power 3 multiplied by delta B will be equal to 259.20 joules, and delta B will be equal to 259.20 multiplied by 2 divided by 150 into 10 to the power 3. So when you solve this, you will get this vertical displacement of point B comes out to be 3.456 into 10 to the power minus 3 meter, or this delta B in meter vertical displacement of point B will be equal to 3.46 millimeter, which is the answer of our this question. And that was all about this problem 14-30. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also share my videos with your friends and help me in growing further. Thank you for your support. Welcome back. In this video, we are going to solve problem 14-31 that is taken from chapter number 14, Energy Methods, and book name is Mechanics of Material by R.C. Hibbeler. Statement is determine the displacement of point B on the A992 steel beam. I is 80 into 10 to the power 6 millimeter power 4. So you can see this is a simply supported beam having a point load at point B, which is 20 kilonewtons. There is a pin support at point A and there is a roller support at point C. So due to this load, this beam will deflect like this. So you have to find this vertical displacement of point B. So let's start with the solution. So what will be the first step is that if you remove this pin support at point A, so you will be having a reaction force, vertical reaction force RAY, and there will be horizontal reaction force which will be equal to RAX. And similarly, if you remove this roller support, so there will be a reaction force, vertical reaction force, which will be RCY. So first we'll find these unknowns by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along x direction must be equal to 0 and force in this direction is taken as positive. So only there is one horizontal force acting in x direction, which is RAX. There is no other force, so it means that RAX is equal to 0. Now we'll use another equation that sum of all moments about point A is equal to 0 and taking the counterclockwise moment as positive. So this is point A. So first moment will be due to 20 into perpendicular distance is 3, and this is producing clockwise, so it will be negative. So I will write minus 20 times 3. The second moment due to this RCY and perpendicular distance is 8, and this is producing counterclockwise moment, so it will be positive. So I will write RCY into 8 is equal to 0. So from here we will get 8 RCY is equal to 60. So RCY will be equal to 60 divided by 8, and that will give you 7.5 kilonewton. Okay. We'll find this RAY by using third equation of equilibrium, that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So RAY minus 20 plus 7.5 is equal to 0, and from here we will get RAY will be equal to 12.5 kilonewton. Now we have all these values. So what we will do is that we will go toward finding the moment equation. So what we will do is that we will cut the beam over here, and this will be the x-axis distance from point A till, and the region for x is greater or equal to 0 and less or equal to 3. And we will draw the free body diagram in order to find the equation of moment. So this is the beam. This is your RA, which is equal to 12.5 kilonewton. This is distance x where you cut this beam. So when you cut this beam, you will be having a shear force that will be V, and you will be having a moment that will be equal to M. This is your point 1. So we'll find this moment by using equation of equilibrium, that sum of all moment about point 1 is equal to 0 and taking the counterclockwise moment as positive. Let we designate it as x1 because we will take another x2 as well. So this is x1. So sum of all moment about point 1. So this will be the moment which will be equal to M. Clear? And this M will be equal to counterclockwise, so it will be positive. So I will write plus M. The second moment is due to this 12 into perpendicular distance is x1, and this is clockwise, so it will be negative. So I will write minus 12.5, and there is a kilonewton. So I will convert it into Newton. So 10 to the power 3 into x1 is equal to 0. So from here M is equal to 12.5 into 10 to the power 3 times x1. And this equation of moment is valid for this region x is greater than 0 and less or equal to 3. Now what we will do is that we will cut this beam at another location, and this location will be distance from x2, and x2 start from point C till distance of 5 meter. Clear? So for x2 is greater than or equal to 0 and less or equal to 5. And this was x1. Okay, now when you cut this beam, so again you have to draw the free body diagram. This is your point C where you have RCY, that is 7.5 vertically, 7.5 kilonewton, and this is the distance x2. So when you cut it, so you will be having a shear force, clear, B, and you will be having a moment in this direction. That is point 2. So what we will do is that we will find this moment by using equation of equilibrium, that sum of all moment about point 2 is equal to 0, taking the counterclockwise moment as positive. So about point 2, one moment is minus m2, which is clockwise, minus m, and the another moment is due to 7.5 into 7.5 into 10 to the power 3 into x2, which is counterclockwise. Their sum must be equal to 0. So moment will become equal to 7.5 into 10 to the power 3 x2. Clear? So this is the moment equation for the region x2 is greater than 0 and less or equal to 5. Now what we will do is that we will find that strain energy due to this moment, which is equal to ui, is equal to integral from 0 to L m square dx divided by 2ei. Since we have divided into two regions for greater than 0 and less than 3, and for x is greater than 0 and less than 5, clear? So we will get this will be from 0 to 3 m square dx1 divided by 2ei plus integral from 0 to 5, and that will be m square dx2 divided by 2ei. Now you can put the values over here, so you will get strain energy due to this bending will be from 0 to 3, m is 12.5 into 10 to the power 3 x1 divided by 2ei plus integral from 0 to 5, m is here, this will be the m, 7.5 for x2 into 10 to the power 3 x2, there will be a square because this is m square, and dx1 is there and dx2 is there, divided by 2ei. If you take 1 over 2e common from both, so it will be 1 over 2 times ei multiply by, you will left with 0 to 3, 12.5 into 10 to the power 3 multiply by x1 square dx1 plus integral from 0 to 5 into 7.5 into 10 to the power 3 x2 square dx2. Now being an engineering student, you should be able to solve this integration. I will show you how to solve using calculator. So what we will do is that I will turn on the calculator and I will show you this equation in the calculator, how to write this equation. So first step is that you will take this integral and here you will put the bracket. First you will write 12.5 into 1000 multiply by this x, and you will close the bracket and there is a square, and limit from 0 to 3, plus there is another integral which is this one, 7.5 into 1000 multiply by again x whole square, and limit will be from 0 to 5. And when you solve this, you can see it is equal to, it will be equal to 3.75 into 10 to the power 9 divided by 2ei. And when you divide it by answer divided by 2 will give you 1.875 into 10 to the power 9 divided by ei. That will be strain energy due to bending. This is how we use this calculator. So now we'll switch this and we will move toward, but again you should solve this by using integral, and if you feel any difficulty you can use the calculator. Clear? So this is the strain energy due to this movement. Now we know that due to this load, this beam will deflect like this. So this will be the delta B, vertical displacement or displacement of point B, and this displacement is equal to this, due to this load the external work is done which is stored in the form of strain energy, and that will be equal to 1 over 2 20 kilonewton 20 into 10 to the power 3 multiplied by this delta B. So this is the external strain energy due to external load. Now I will write this strain energy due to external load will be 1 over 2 multiplied by 20 kilonewton, so 20 into 10 to the power 3 multiplied by delta B. So this is your equation number 1 and this is your equation number 2. So what we will do is that by using conservation of energy, this ue is equal to ui. So 1 over 2 multiplied by 20 into 10 to the power 3 into delta B will be equal to 1.875 into 10 to the power 9 divided by ei. So what we will get is delta B will be equal to 1.875 into 10 to the power 9 multiplied by 2 divided by 20 into 10 to the power 3 multiplied by I is given as 80 into 10 to the power minus 6. That is in meter power 4. And what about E? So E for A992 steel. So we will go to the book A992 steel. You can see A992 steel, E is 200 gigapascal. So note down this value as well, 200 into 10 to the power 9. Now you have final value. When you use calculator and you find this value, you will get it 0.0117 meter. Or in terms of millimeter, this vertical displacement of point B will be equal to 11.7 millimeter. And this is the answer of this question. And that was all about problem 14-31. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. Also share my videos with your friends and help me in growing my channel further. And if you have any question, you can ask me in comment section. Thank you for watching.